So what we're going to do today is continue this very basic exploratory descriptive part, although today we're going to get a little bit more mathematical towards the end. So last time I dealt with traditional statistical graphs and tools of exploratory data analysis. Today we're focusing on the geographical part, on the mapping part. And it's a lot of material, but it's all really easy. It's just different types of maps and different types of visualization things, except I do want to spend some time on the issues related to mapping proportions or rates, which really has to do with risk mapping and identifying locations of elevated risk. And this is a little bit more mathematical, a little bit more formal. So I'll probably spend about half the time on that. And in the beginning, so I'll go over just a refresher of some of these concepts, basically emphasizing the notion that it's not about making maps, but it is about using the map as a visualization device to interact with the data. And we'll see in the lab specific ways in which we do that in GeoDa in particular. Then, because I realize most of you have not had much exposure, if any at all, to GIS or map making, I just want to give you some very basic design principles for making maps. The reason I do this is that this day and age, most software has pretty decent defaults, but I've seen some really awful maps, and I've seen some uses of legends that are completely inappropriate and color schemes that are completely inappropriate for particular types of questions. So this is not by any means cartography or map design in detail. You can spend a whole course on that, but it's just some basic principles that, of course, GeoDa conforms to, but some basic principles that if you make maps, say if you use R to make maps or something similar, you should be aware of. And then we'll go over a couple of different types of statistical maps. A map is really, if you wish, the spatial representation of a histogram. We talked about the histogram last week as a way of giving a discrete approximation to the distribution of the data. Well, a map, a choropleth map, is really a discrete representation of the spatial distribution of the data. And so this means that we have to somehow cut this distribution, and the cut points are important, as we'll see in this brief discussion of statistical maps, and then we get into the more technical material of risk mapping. So these are the terms we talked about a little bit last week. Mark Momonier is a famous geographer and cartographer at Syracuse who's written a lot about maps and how to lie with maps. It's a really, I'll talk about it in a few minutes. It's an interesting little book. But the whole idea is to go beyond just the map as a presentation. So traditionally, and still unfortunately in a lot of data analyses, the map is constructed at the end of the day. When you're done, here's a nice map, this is what I found. That's not what we're doing. We bring the map in the exploratory process as one, as we saw last week, as one of the views on the data. And then we arrange these views, we focus, we interact with these views. And so you have a bunch of buzzwords out there: geovisualization, geospatial visual analytics, exploratory spatial data analysis, which is my favorite for obvious reasons, has become obvious soon. But they're all basically about the same thing. They're all about using the dynamic graphics, which is the principle we saw last week, introducing the map as part of the dynamic graphics. So we have linking, we have brushing, we have zooming in, focusing out, arranging multiple maps, and that's what it's all about. It's about learning from the data and using the map as a visualization device to learn from the data. So there's quite a bit of literature on this. Mostly from a geographical perspective, disciplinary perspective. The term geospatial visual analytics then comes more from the computer science world. We saw last week the idea of detecting the expected and discovering the unexpected. It's the same thing, but we bring in the spatial dimension, not just as a picture, but as a dynamic part of the exploration of the data. And as I become more familiar with GeoDa as one example, that's the whole idea behind GeoDa, is interacting with the data to extract information, knowledge, wisdom, this progression. So that's my thing, exploratory spatial data analysis. It's really about spatial distributions and where the data are. And is there anything interesting or special about where the data are? And why would high values occur in similar locations or not? Or why would particular values be surrounded by similar values or not? Why would there be structural breaks in the data? Remember, it's an exploratory process. This is what we do to build hypotheses, to come up with ideas about what may be going on in the data, and then we formalize that further and put it into formal models when we do the spatial modeling, which is not part of this course. So there's some interesting concepts here. So traditionally, there's kind of two directions to going at knowledge discovery. One is the traditional formal, the kind of theoretical approach that you see in classic disciplines like economics and sociology, political science. You have a hypothesis. Typically, you write it down as an equation or a system of equations, and then you get some data to see if this stuff actually holds in reality. And so then model first, data later. Then the inductive approach, which is more of the Tukey type of approach to learn, is the other way around. And that's also more of the data science-y approach that, if you read that article, it's been around for 50 years, but it's basically a driven approach to knowledge discovery. So the data first, the hypothesis later. It's an inductive approach. And then in this whole visual analytics world, there's an alternative concept that this process, not directional, data first, theory later, or theory data later, but both happen kind of and feedback off each other. And the main idea there is what some people have called a visual pop-out. And this is kind of an aha moment. And you know it when you see it. Okay, this is when you are interacting with the data and all of a sudden the light bulb goes off, something occurs to you. So this is very different from this kind of one linear, one directional approach, either the traditional one or the more data-driven one, but it's more of a going back and forth, and it's interacting with the data, and at some point, as I always say, some people do, some people don't. A lot of this has to do with experience. A lot of this has to do with creative combinations of different views of the data. And as we explore more and more of these views, you'll get better and more creative at combining them, and then hopefully you'll have more of these moments of discovery. So this is kind of the process of knowledge discovery. Geovisual Analytics fits into this. It combines concepts and techniques like dynamic graphics, brushing and linking from visual analytics, and then brings in the map as one way to interact with this. And we'll see examples of this in the lab. We'll have interactive mapping. We have animation, linking, brushing. We're already familiar. I know I'm going really fast because the interesting part comes, and I want to spend time on that. If you want to know more about the thinking behind this and some really cool examples, I suggest you visit this website at Penn State. There's a that does a lot of this kind of stuff, of course, other than our center here. I did want to say something about how to lie with maps. And as I mentioned, and as I'll go over fairly quickly in a few minutes, there are a couple of very important design parameters when you make a map. Things like the scale of the map, the cut points, just like in a histogram, what kind of legends you use, what kind of colors you use. Very importantly, the choice of the projection. And a lot of you, I know, are not familiar with projections, and as I've already mentioned, you know, the Earth is not flat, the maps are. So how you go from this 3D object to a two-dimensional flat image is a mathematical transformation. That's basically what it is. And we'll talk about it in a second, but there are no transformations that reflect everything properly, meaning the distances are right, the areas are right, the directions are right, and so on. So something needs to be sacrificed. And it's important, you know, as a map maker, you don't really have to worry about that too much, but as a map maker, it's important to know the implications of the choices that you make. And this is exploited in political maps. For example, how would you rate the size of Greenland relative to the size of Africa? Okay, most maps that we're familiar with that have Western type projections have Greenland almost the same size as Africa because of the projection. And it's actually a fraction of the size of Africa. So this is an example of how a projection distorts the area in the 3 dimensions as represented in the 2 dimensions. And there's another example that I was going to talk about later, but I might as well bring it up now. It's an example of distance. And there's a famous or infamous, depending on your point of view, with geographers it's infamous, article in The Economist, the magazine The Economist, about, and this is actually more current than I'd like it to be, about the range of North Korean rockets. And so it's a little map that shows, you know, North Korea and a little circle around North Korea. And so basically, you know, this is not going to go anywhere. Only the map is in a Mercator projection, which completely distorts the distance. Then the circles actually reach the US. And it's totally different impression. Now, you can manipulate this, right? And if you're a political cartographer, and there's really interesting examples of this in the, actually in this little book, How to Lie with Maps of Mark Monmonier, there are very interesting examples of how distortions of scale using particular projections, centering the map on particular countries or continents. I mean, why is Australia always, I mean, it's actually upside down, right? But that's how we present the maps typically, with the north on top and the south on the bottom. There's really, mathematically, there's no reason to do that. It's not like we're standing, you know, facing north. I mean, you stand the same way in Australia, but you're facing the opposite direction. So it's purely conventional, it's purely cultural phenomenon to do it that way. And so in the Second World War, in the Cold War, there's classic examples of maps that make bad countries look way bigger than they are, and et cetera, et cetera. This is a fairly current example, and this is, if you go to this website, there's more examples of this as well. This, in a nutshell, makes it look like all of Chicago is being foreclosed. Chicago, and the red dots are the foreclosures in Chicago. Now, the reason you get this impression is completely misleading. It's only due to the size of the dots used on the map. If you use much smaller dots, then it won't look like this at all. So again, it is one of the parameters of map design that can be manipulated. I'm not saying that it was in this particular instance, but it's probably more like an oversight. Somebody uses the default dot size in the map, and all of a sudden it looks like all of Chicago is foreclosed, and it really isn't. So these are some things to think about, and as I said, this is not a cartography lecture, but I do want you to at least know what to think about and what to look for. So first of all, vocabulary, it's choropleth map, not chloro. I know a lot of you are conditioned to say that. I don't know why, but it's choro. It's from region, and region, an area on the map. It's nothing to do with chlorophyll or green or chloride or anything like that. Right? It's a spatial distribution. The path maps, as opposed to point maps, deal with areal units or regions. So we somehow have to reflect the distribution of the variable of interest where it occurs in space. And so typically, in most practical situations, the only way to do this is to cut up the distribution into bins, just like we do with a histogram, but here the bins will reflect colors in locations on the map, in a choropleth map. So we need to figure out how we're going to define these bins. And here again, many different options, many different choices, actually just like with the histogram, but with the histogram we don't talk about it that much. So the things to keep in mind is, besides this classification, which is very important, is that design parameters. So I already talked about the projection. The four aspects that cannot all four be reflected properly by means of a projection are shape, area, distance. So if you're interested in making a map for navigation, so if you sail across the ocean, you find your way, you want to use a projection that keeps the directions right. If you want to find travel distances, you want a projection that keeps the distances right, right? If you want to reflect the shape of the countries or the continents properly, you want to make sure the shape is right, and so on. So you can't have it all. One of them is going to go. So if you have the distances right, you may not have the areas right, or you may not have the shapes right. So this is a trade-off you make, and we don't have time to get into this, but I mentioned the other day there are thousands of projections, and there's a website which we'll use in one of the labs to guess a projection. Besides a projection, and these two are often confounded, is this whole area of geodesy. Geodesy is about measuring the shape of the Earth. And just to kind of make you think a little bit, when you say my location is X feet above sea level, what is sea level? How do you measure what sea level is? There's gravity. The moon pulls the water up where it's closer to the Earth, so then the water is lower on the other side. So there's actually no such thing as the sea level. It changes constantly. So you need conventions and very precise tools to actually figure out where you are on the Earth. And that needs to be reflected in the maps. Scale is important, makes things look smaller or larger depending on what you want. Color and legend. We'll talk a little bit about classification, color, and legends, because these are the kinds of things that are easy to manipulate, and you can easily make mistakes if you wish. So the classification is about how you cut the distribution into pieces. One choice is not to do that at all, and that's a continuous representation. And for all practical purposes, that doesn't work for large data sets because you don't have a fine enough gradation. So you can have a continuous color ramp, but very quickly you can't tell the difference anymore. You can try this. A lot of the mapping programs have these color ramps, and if you have too large a range of the variables, you basically can't see it. And in the days, cartographers came up with different kinds of cross-hatching, different line schemes to show different values, again, in light of a continuous distribution. But here as well, this doesn't really work if you have 3,000 observations. It works for 20 or 40, but it doesn't really work. So then an alternative is to use symbols. So you still have your map. Let's say we would have a US county map, but instead of using a color ramp or something else, we would put little bars on the counties. And so the larger bars are higher values, the smaller bars are smaller values. You might have seen maps, marketing firms like to use these with little pie charts in locations. So that's basically a symbol map where you don't discrete cutoffs, but you can use the full range of the values. But then you give up some of the representation. Again, there's a perceptual issue here. If you have too many of these symbols on the map, you can't see them anymore. There's really, there's two constraints when you make maps. One is, so how many, a pixel is a picture element on the screen. And so the smallest thing you can represent is 1 pixel. So if 1 pixel is the equivalent of 200 by 200 miles, then whatever happens within these 200 by 200 miles is represented by a single little dot. And so you have to keep that in mind. That's one limitation in the big data world. The other limitation is you. You can typically, depending on how well you're trained and which study you read, you can look at 5 to 12, maybe a little bit more stimuli at the same time. So even though technically you could have 25 maps open on the screen, you can't handle it. You're only focusing on a subset of these things. So that's something else to keep in mind in this kind of visual analytics world. So in terms of classification, the histogram counterpart, equivalent, basically we have to figure out the size of the bins. So we have the range, smallest value to largest value. We have a continuous distribution in there. Where do we cut? And there's a lot of traditional ways of doing this. You may have heard or seen equal interval. Equal interval is exactly what it says it is. So you take the range, just like we saw the other day. You have 5 bins. You divide the range by 5. That gives the size of each of the bins, and then whatever falls in there, falls in there. You can, of course, set it manually, just like I alluded to in the lab. In GeoDa, you can do this. We'll see how that works in the lab next week. But that is typically appropriate. I can think of 2 cases where that is very, when you want to look at things over time. So you want to use the same cut points and you want to see how the distribution changes over time. You don't want these, most of these things are relative. So therefore a cross section at one point in time, say if you have 5 equal intervals, everything will have 5 equal intervals, but the range may change from one period to another. So if you don't want that, you set fixed cutoff points. And the other instance, which I mentioned in the lab, is one, your cutoff points somehow have something to do with particular rules, institutional setups, legal requirements, things like income categories, for example, used for taxation. You want to use those. You don't want to use the arbitrary equal intervals or something else. Natural breaks is basically k-means clustering in one dimension. We'll talk about k-means clustering later on. Some of you may be familiar with that. It's a grouping method that groups to maximize internal homogeneity. So let's say we want 4 categories. How do we group the observations into 4 categories so that internally they're the most similar? And hence the term natural breaks. We break them where the groupings that result are internally most similar. As a result, some of these groups may be kind of weird. Some of the groups may have a lot of observations in them, and others may have very few, even just 1, because they maximize. So an outlier, for example, is likely to end up in a category by itself because it doesn't fit closely with anything else. So there's pros to all of these approaches. And then we can use statistical criteria where we use the basically the statistical description of the distribution of the values to inspire the categories that we use. And we've already seen the example of a quantile map. So quartile is a common example. You sort the data from low to high. You take the midpoint, the median, first 25%, first quartile, then 75%. So you end up with 4 categories. Each of these categories, in an ideal world, we'll see later that it's not always ideal in the lab. In an ideal world, each of these categories has exactly the same number of observations. Here again, this may not be ideal if you look at a variable over time, because the categories will always have the same number of observations. Even though, let's say with a crime rate goes down over time, the maps will look the same. If the high crime areas remain the high crime areas, but they may have a much lower crime rate in later years. And how do you reflect that? You cannot do that with a quartile map. So this is where you have to think which kind of criteria you use. Then a counterpart of this with a more parametric approach is the standard deviation map, where you standardize the data and you make the cut points correspond to one standard deviational unit. So then again, we have an easy and intuitive interpretation of the notion of an outlier when you are more than 2 standard deviations away from the mean. And this allows us to create some maps that emphasize extreme values. And we'll see some examples of that. One example is a box map, which is my favorite device. Okay, so we have these kinds of things. You have a histogram, obviously, that corresponds to a map classification. We'll do a lot of these in the lab. I don't really want to spend too much time on this here, but they're not the same depending on the criterion. These maps all emphasize certain aspects of the data slightly different. Okay, colors. Colors are really dangerous because they have value attached with them. Red is danger. Red is bad, right? So beware of what you color red. You don't want to make any implications that are unintended. Now, of course, in political maps or in, the manipulation of the map, the use of the color is one of the things that can be manipulated to highlight. You saw the red dots with the foreclosures in Chicago. There's a reason why this is dot. They want to make a point. Hey, something really bad is going on here. Let's make it red, not light blue. Light blue is much nicer, is more comfortable, is typically a cold color. So the color interacts location of the values to give you a different perception of patterns. So you can use this, you can abuse it, you can misuse it. A former colleague of mine, Cindy Brewer, has done a lot of work on the perception of color and which colors are good to go together in maps. And she has a website called Color Brewer, and it's really cool in terms of, if you've never thought of this, you should go visit it and start looking at some of these examples, because she's actually done a lot of work based on the psychology of perception of what goes together. So you see some examples of these color schemes which either combine different hues, like on this left side, and then or are different shadings of the same hue, the same base color. And this has a lot to do with legends, because you choose the colors to represent the values in different categories, and these are in a legend. And there's, in broad terms, 3 categories of legends, 3 types of legends. The first type is, and it's very important that you don't mess these up, because they present different types of information. So the first one I talk about is called a sequential legend. There is a natural ordering of the data from low to high, low crime to high crime, low income to high income, right? This is not appropriate for categories. Voting Democrat, voting Republican. There's no ordering in here. These are categories. So do not use a sequential legend for that, right? And then, again, color brewer schemes appropriate for different kinds of sequential legends. And you see in the website, you can pick this and you can look at different kinds of color schemes and then get the codes, the RGB codes or whatever other codes. And then, for example, if you want to make your map in R, you look it up in here, you get the codes, and then you use the codes in R when you make your map, right? And the map will look great. The other thing to keep in mind, and I'm sure you've run into this, that what looks great on your screen doesn't necessarily look great on the projected screen and may look terrible on paper. So each of these media has its own sets of color schemes that are appropriate to reflect information. And that is something to keep in mind, even though I don't keep it in mind. I focus on what looks good on my screen, but I realize every once in a while you can't see anything on the projected screen because the colors are just not coming out. So this is sequential, low to high, right? Then this is diverging. So one is divergent, for example, if you're interested in showing standard deviational units. So you have the mean, and we're moving away from the mean. So even though it's low to high, we're really emphasizing what is the central tendency and how we are extreme moving away from that central tendency. So that's a different scheme. As you see here, it starts with something in the middle that is fairly neutral, like something similar, and then it moves in two directions. Typically, one direction is reddish or brownish, the other direction is going to be bluish or orange. But don't ask me because I can't tell green and blue apart very well. So I swear I have a green couch and I've been told it's not green. So, but that's something to keep in mind, of course, if you want to make your maps and views accessible. You have to think about how people with, for example, who cannot distinguish colors very, very well, how they can get the message from your map. And, you know, similarly, visually impaired people, I mean, we tend not to think about that too much, but it does matter. And, you know, there are some rules that you can follow to be accessible. So then, big difference. Both of these have to do with values that actually mean something. At the very least, they're ordinal. They have a ranking. But a lot of the information that we deal with is not ordinal. It's simply categorical. And you cannot, or I should say, you should use legends that suggest ordering with categories, because there is no ordering for the categories. That is not appropriate. You suggest for the you really shouldn't do. So the same thing happens when you code your categories 1, 2, 3, 4, 5, and then you throw them in a regression and you say, oh, 5 is more than 4. Well, it's not. It's just different. That's all. So you have to be very careful with this. And you see the color schemes that are appropriate for these cases. They're really designed not to prefer one category over another, because that is really the objective. When you have a categorical scheme, you cannot favor one group over another group. They're just groups. And you want to the differences or the similarities between the groups, but not any kind of ordering of the groups. So that's kind of in a nutshell everything you ever need to know to make a great map. You know, the big one is Color Brewer. It's very easy to use. Go find that you like for the kind of legend that you need, and you're in business. Of course, all the GeoDa maps follow Color Brewer, unless you start messing with the colors yourself. Okay, some statistical maps. Again, I can go fairly quickly with this, I think. It's pretty straightforward. A quantile map is just the notion of a quantile but applied to the colors of the map. So as a result, you have equal number of observations in all of them. You've already made a quintile map in one of the labs. We'll make more of these next week. There's a big practical issue I illustrate, and is the problem with ties. And this is one of these instances where spatial thinking is very different from standard statistical thinking. In standard statistical thinking, a tie in a quartile distribution isn't really a big deal, because let's say we have a cut point of the 25 percentile, and we're looking at, income per capita in kind of broad categories. So let's say we have 100 observation. So observation 23, 24, 25, 26 have per capita income of 1,000. What's the first quartile? 1,000. No problem, right? Now in a map, we do have a problem, because quartile number 1 has one color, quartile number 2 one color, right? And here we have, 24, 23, 24, 25, 26, 27. Which of these 5 are we going to put in category 1 versus category 2? That's completely arbitrary. In fact, they should all, because they all have the same value, they should all be in the same category. Which one? The lower one or the higher one? There's no real preference. This is a problem that actually happens amazingly a lot. It happens when the distribution has big flat parts to it, where a lot of observations have the same value. Then the odds that a cut point is where you have ties on both sides go up. And then you have to basically move all the observations from the lower category in the higher category, or vice versa. This happens a lot when you have a lot of zero. So, for example, when you look at homicides in the US, or diseases, rare diseases in the US, county level, little small area level, you'll have a lot of observation with 0. And you can, if you make a map, say you make a quintile map, 20% of the data, if 30% of the observations have 0 as their value, your 20% cutoff cannot be decided. So then the lower quintile might have no observations in it, and then the second one might have twice as many in it than it should. And so whenever you make a map, for example, in GeoDa, it will automatically do this classification and bump them up to the next higher category. But if you look closely at the left, you might see that some of the lower categories have 0 observations in them. That's due to ties. So ties are bad for quantile maps, even though quantile maps are some of the easiest maps to make, and we'll see a lot of examples in the lab. Box map is something I came up with, and obviously I like it a lot. It just occurred to me that a quartile map, which you see a lot, misses something. Because when you look at a quartile distribution, any distribution, there may be outliers. And a box plot, as we saw last week, is a way to identify these outliers in a quantile categorization. First quartile, the third quartile, the interquartile range. We have our fences. Whatever is outside the fences, we call an outlier. A box map, same idea, choropleth map classification. So in the first quartile, there are some observations that may be outside the fence. We color them differently. And similarly, in the fourth quartile, there may be some observations that are above the fence and them differently. So even though, in essence, it's a quartile map, it actually has 6 categories. So the 2 outliers at the top and at the bottom, and then the other regular quartile categories. And this is very useful to visually identify what might be potential clusters right away. So if you have outliers, outliers are extreme values, right? They could be coding errors, or they could be systematically higher observations, like in the New York City example that we'll be using in the lab. You know, Manhattan is very different from the rest of New York City, you know. So, and that comes out. But think about it, you know, you're from Mars, you don't know anything about New York City. Why would these outlying values, these really extreme ones in the box plot, why would they all be next to each other? You know, that is a spatial question. The non-spatial statistic, the box plot, tells you these are outliers, all well and good, but the map tells you where they are, and everything else being your null hypothesis would be that one could be here, the other one there, the other one in another place. There is actually a priori no reason why they should all be together. So if they are all together, that raises a question. That is your pop-out, your visual pop-out, your aha moment. Why are they next to each other? What is going on there? Why might that be a, what we call a cluster? So we can do the same thing with the lower outline. We can do the same thing with the idea of a standard deviational map, where again, this is an example of a diverging legend. We start at the mean and we move out, and as we get more standard deviational units away from the mean, we identify outliers. And in the standard deviational map, you can have categories of outliers, you know, 2 standard deviations, 4 standard deviations, and more. You know, you may have heard of these sigma rules, you know, 6 sigma, and there's a couple of other variations that has to do with minimizing in quality control the observations that are more than so many standard deviations from what they should be. So you have a robot machine that cuts pieces of steel for a car. They have to be this many millimeters long. You know, how much deviations will you tolerate? Because there will be deviation. You know that. It's just a random process. It won't be perfect. So how imperfect can it be before it doesn't work anymore? And that's a very important statistical use. So these, again, you see the diverging colors going to the blue, the low values, and to the reds for the values. Cartogram. Who's familiar with a cartogram? Okay. So it's actually a good thing that I talk about this, because I'm always assuming that this day and age most people will have seen a cartogram, and actually I bet you that you have, but you didn't realize what it was. So one of the problems with standard choropleth maps is that the area on the map, the size of the little polygon, is representative of the physical area of that unit. And I always give the example of homicides in the US. And some of the cities with the highest homicide rates in the US are like St. Louis, New Orleans. On a map of counties of the US, you'd never see them. They're teeny little areas. So they are the most important in terms of the information you're trying to portray, but they're essentially invisible. So a cartogram fixes that by changing the geography. So rather than making units, the polygons, representative of the physical area, they become representative of the value of the variable that you're trying to portray. So homicide rate, New Orleans would be a big shape. St. Louis would be a large shape. And all these counties in the northern Midwest that basically don't have any homicide except for Fargo, they're very teeny. You basically don't see them anymore, right? So there are some very creative ways of doing this. And the one we implement is a, what is his name? Doring, something like that. Dorling circular cartogram. So it's a kind of ingenious algorithm where you try to represent, in this case, each subborough of New York City by a circle. The size of the circle is proportional to the magnitude of the variable that you're portraying. So in this case, it's rent. So bigger circles, more rent, smaller circles, lower rent. But by the same time, we want to put these circles as close as possible to where they are geographically. So this is a very complicated nonlinear optimization problem where you try to match the neighbor structure of the circles to the neighbor structure of the physical aerial units that they correspond with, have the size of the circles be proportional to the variable. So this algorithm basically bounces these circles around with some tension measure that reflects the optimality of the arrangements. Sometimes it's good, sometimes it's not. So sometimes, you know, you see all these circles, you have no idea which is which. And for example, all the dark red ones represent Manhattan. So, you know, with some imagination, you can see Manhattan, but sometimes you can't. With US map, with Florida, Florida can end up in really weird locations depending on the variable that you portray. As I mentioned, there's lots of different variations on this theme. This is a different algorithm, more or less their actual position, and then uses the size of the, I mean, it's not a rectangle, but it's kind of a squarish thing to represent the value. And you see this a lot. You may actually, I saw one just the other day in the New York Times having to do with the representation of, you know, seats in the Electoral College and the actual population behind it. If you want to somehow show, the point of the article was the overrepresentation of rural America versus urban America. And so in a map that shows the actual areas of the county, you can't see it. But if you morph the counties as a function, you see that the middle of the country becomes teeny and the coasts blow up because that's where the population is. And that's one way of portraying this. Some people get really creative with the shapes of these cartograms. And then, as I mentioned, extending this notion of a trellis graph or a conditional plot, we can do the same for maps. These are called conditioned choropleth maps, or a micro map matrix is the same idea. We have two axes to condition on a variable that makes subselections of observations, and then we only show those observations in the cells. So just like we have done this with the scatter plots in the lab the other day, we can do the same thing. If there is no interaction effect, then all these little maps should basically look the same. They should have similar proportions of blues and reds and browns. But if all the browns are in one corner and all the reds are and all the blues are in another corner, then evidence of interaction. So we've already seen this principle. This just extends this principle to the use of a map to visualize data. And then finally, very quickly, map animation is just basically moving through the values. I can't really show this very well here. We'll do that in the lab. So now we get to a little more conceptual and mathematical, if you wish, topic. And it's very important for those of you interested in public health applications or anything where you're interested in portraying spatial discrepancies in underlying risk. This is, for example, hugely important in the insurance business. There's huge differences. I mean, you may not realize this, but there are huge differences in claims for the same things between geographic areas of a city. Some areas are just constantly claiming, and other areas, same thing, never file a claim. And so if you're an insurance company, you want to know that. You want to know these patterns and understand it. So basically, it's all about risk. what is the underlying risk? What is the probability that an event might occur? You know, what is the probability that your house catches fire? You know, so how do you figure that out? What is the probability that you get into a car accident? What is the probability that you get a particular disease that will require a certain treatment? How do you figure that out? Basically, you don't know. You don't know what the underlying risk is. We all have some risk of getting a whole range of different diseases, but some of us get them, some of us don't. And get a handle on this underlying risk, because that's really what we understand for purposes, for modeling purposes, for predictive purposes, or just to understand a phenomenon. So we have to find a connection between what we observe, which are events, people being sick, people getting into accidents, houses burning, and then the underlying risk, which we do not observe. So it's all about estimating risk, and how are we going to estimate this risk? And a very, as it turns out, somewhat optimal approach is what we probably would just think of is, well, you take the number of times something happens, you divide it by the number of times it could have happened, and that is an estimate of the probability. That's an estimate of the risk. And that is called a crude rate or a raw rate, and is basically the ratio of the number of events over the population at risk of the event. Now, this may sound straightforward. The event part is easy. The population at risk part is not easy. And that requires some thinking somewhere. Let me give you an easy example that is actually very complicated. Crime rate. Okay. Crime rate, event part, we know. Number of arrests for this or that or the other. What is the denominator? Is it it's the population risk, right? So if you're interested in the risk of getting your wallet stolen walking in a downtown business center, what is the population at risk? Is the people who walk downtown, right? That is not the population of the downtown in the census, because that's often close to zero. Nobody lives there, right? So how do you get an estimate of the true population at risk? Conceptually, it's straightforward. In practice, not necessarily. In practice, you really have to think, and it matters, because your estimate of the risk, of course, depends on both parts. It depends on the numerator, the easy part, the events, but also on the denominator, the population at risk. So if you underestimate the population at risk, you overestimate the risk, everything else being the same, and the other way around. So as it turns out, I don't want to get too technical, this crude rate, in some sense, is optimal. It's the maximum likelihood estimate. Maximum likelihood is, in classical statistics, the gold standard is unbiased, meaning on average it's on target. So on average, you get the right estimate of the risk. But there's a problem with it. We'll get to that later. So why are we interested in this? We're interested in what I call spatial heterogeneity. Everything else being the same, the risk should be uniform throughout. It shouldn't really matter where you live. Your chance of getting a particular disease should be the same, unless there are factors that affect these locations differently. For example, air quality, pollutants, chemicals in the water, in the soil. So that results in the risk not being uniform across space. Before you can start understanding why this is the case, or start understanding some of the causal factors behind this, you have to identify that the risk is not uniform. And so you have to, in a nutshell, make maps of the risk and then identify locations that, in some sense, might have an elevated risk or a below average risk. And so that's what it's all about, right? So at face value, this seems like a pretty straightforward exercise. We get the event, we get the population at risk, we divide them, we get the the estimate of the rate, and we make a nice map of the rates. And where the rates are high, we have a problem. Where the rates are low, everything is good. Well, it's not that simple. So let me first give you an example to illustrate one of my pet peeves, and is not to make maps of total counts. Okay, so this kind of illustrates this. Look at the two boxes that are highlighted, one in blue, of foreclosures by census tract, I believe. So according to this map, these two areas have fairly high counts of foreclosures. But then we also have a map of the number of housing units. So we're going to compute the risk. The population at risk here is not people, but houses, because houses are foreclosed over how many houses there are. And so you see one of these has a lot of houses in it. It also had a lot of foreclosures. The other one doesn't have very many houses in it, but it did have a lot of foreclosures. So then, of course, if you make the ratio, it changes in that this houses foreclosures becomes actually an outlier, an element. The other one with a lot of foreclosures is kind of middling, right? That's why this is a spatially intensive variable. The count of foreclosures is spatially extensive. Does that mean if the denominator, the population at risk, is roughly stable over space? So if you have units that are delineated to have a constant population, then whether you do something per capita or the actual count basically doesn't matter. But if the units have very different populations, then it does matter. And we'll get back to this in a second. So the first note, so we have our crude rate. How do we know whether something is elevated or not? And this is a notion, those of you who've done some demography may be familiar with the notion of a standardized mortality rate. So basically, we're trying to figure out when a rate is high. And we're going to say it's elevated when it's higher than some kind of standard. And where does the standard come from? If you're a Bayesian, it comes from your prior distribution. If you're a practical person, it comes from, not that Bayesians are not practical, it comes from a reference distribution. So typically, you have data for the whole country. You have all the cancer cases in the whole country over, and let's say some very rare, all the cases over all the people. That gives you an estimate of the risk nationwide of having this cancer. And this is what, by the way, insurance is all about pooling risk. So the more of these people you can put together, the better you can cover the risk. If you're just by yourself, you're in trouble, right? So given that reference rate, how can we compare the rate that we have, say, in a little county in the middle of Minnesota, to this reference? Are we high or are we low? Right? And so that's the notion behind a standardized mortality rate, or an excess risk rate in different fields has different names, but it's basically the same. So we need to get this average risk. It's important you keep in mind that this average is not the average of the rates. So we have a nice map. We have our rates for every county. The average of all these rates is not the rate for the state. It would be if you weighted each of the counties by its population, but the simple average doesn't do this. A weighted average would. So instead, we can just add all the cases together and add all the people together and take that ratio. So that is our reference. That is our point of reference. So to do this a little more mathematical, let's say O sub I are the number of events that we observe in unit I, and P sub I is the population at risk in unit I. And then the crude rate or raw rate at I is simply the ratio of OI over PI, right? And this turns out to be also the maximum likelihood estimate. It's unbiased and all that good stuff. The average risk is not the average of the OI of the RI, but it's the sum of all the events over your reference group and over the sum of all the populations, right? So now we have this average risk, and we're going to compare our actual observed risk to this average risk. And how do we do that? We do that by figuring out how many events would we have in our area if the average rate would apply. Let's say if the average risk is 1 per 10,000, we have 30,000 people, we would have 3 cases. We have 50,000 people, we would have 5 cases. So this is actually standard practice in epidemiology and in public health to get a reference. So you take whatever group you think is of interest, the whole state, the whole country, a whole ethnic group, whatever is relevant for the question at hand, that becomes your reference. Then for each small area, this is called small area analysis, you multiply their population at risk by this average rate. And that says, everything else being the same, this is the number of events that we could expect to happen in our small area. And then you compare what actually happens to that expected number. And that ratio is called a standardized mortality ratio, SMR, or an excess risk, or any number of terms, but it's always the same thing. So it's very simple. You have the observed events, then you take your population at risk, multiply that with the average risk, and that says, this is how many events would happen if the average rate would hold for us. If we have more, we're in trouble. If we have fewer, we're doing better, right? So you look at the average rate of car accidents in a whole city. Then you look at a neighborhood. You have the number of cars in the neighborhood. You multiply that by the average risk. That should give you how many accidents you could expect to happen in that neighborhood. And then you compare that to what actually happened. So it's very simple, but it's very powerful because it compares your crude rate to the rate on average, or you compare your actually observed events to what the expected events would be. And it's very simple math: larger than 1, elevated, less than 1, not elevated, and then we can make a map of this. And that's our excess risk map. And here again, we see our 2 boxes. The one, nothing going on. The other one is identified. This is a place where there are way more foreclosures than would be the case if the average for the city as a whole were to apply. That's the idea. Okay, now comes the hard part for the end. A little bit of math. The events, we think of them as a number as draws from a binomial distribution. And you can think of your stats lectures. You have your bin, white balls, red balls, 40% white balls, 60% red balls. You draw 10 balls, how many of them are white, how many of them are red? That's basically the problem, right? So you have a population, people have the disease, people don't have the disease, any kind of number that you draw from that group, how many can you expect to have the disease? It depends on the underlying probability, which is pi. And so this is the standard binomial distribution equation that give you the probability of having X events out of a population of P given the probability pi. And so it's pi to the X and the complement 1 minus pi to P minus X. And pi is between 0 and 1. So the mean of this distribution, you'll see in a second where I'm going. The mean of this distribution is pi times population. And the variability, the variance of this distribution, is pi times 1 minus pi times the population. So these are characteristics of this binomial distribution. They depend on two things: underlying probability pi, the other one is the population. Right? So it's the same thing. Is the probability is 0.1, and you have a population of 100. How many events can you on average expect? 0.1 times 100 is 10. That's what this means. Okay. So now we're getting a little more complicated. We're really interested in finding out what is this crude rate on average. So the crude rate is the ratio of the number of events, that's the random part, and the population, which is not a random part. So if it's not random, it's fixed. It doesn't change. There's no variability. So in our calculations, we can't ignore it, but it doesn't change. So it doesn't have an average. It doesn't have a variance. It is what it is. It's P. So the rate is the ratio of the events, O over P. And the average, the expected value, as it's called, the E thing, is the expected value of the numerator divided by P. P is just a constant. And we just saw that the mean of the number of events given a binomial distribution with population P and probability pi is pi times P. The ratio is, lucky for us, pi. So on average, the rate, the ratio of the number of events over the population, is correct. It has the actual underlying risk pi, which we don't observe on average, right? That's why it's called unbiased. On average, it's right. Okay, what about the variance? Again, variance of the numerator over P squared. For variances, you have to square it. So we plug in these values. We see now that there's P in the numerator, P squared in the denominator. So we divide by P. And here's the catch. This means that whereas the mean, average, just depends on the probability, which is what we want, the variability of that estimate, in other words, how precise it is, depends on the pi, on the underlying risk, but also on the population. In fact, it's inversely related to the population. In other words, the larger the population, the smaller the variance, the more precise the estimate of your risk. The smaller the population, the larger the variance, the less precise is your estimate of the risk. And you can think of this, right? If you have you're looking for a very rare disease, right? There's not going to be too many cases, so you'll get the rate right with a fairly high precision. But if you live in a small town, you may not have anybody with that disease. Does that mean the risk is zero? No. It just means your estimate isn't very precise. And the true risk is something else, and you're just estimating it by the mean, but you're off, right? So you can illustrate this, just a little example. If you have the pi as 0.1 and you have one population of 500, then the standard error is 0.013. If you have population of 100,000, the standard error is 0.0009. So you see very quickly when you have large populations, these standard errors become very small. It becomes very precise. When you have small populations, you're in trouble. So that's where this idea of smoothing comes into play. And it's actually becoming very important in modern data analysis, in big data analysis, in statistical learning. It has to do with borrowing strength, which is a very Bayesian notion. A lot of you are not familiar with Bayesian statistics, but it basically means, why trust my estimate in my little county when there's all this other information out there from other studies or other larger reference areas that tell us something about what the true unobservable risk might be. And we know that our estimate for our small area is very imprecise. So can we do better? Can we do better by giving up a little bit of the unbiasedness in return for higher precision? And this concept is a concept of bias-variance trade-off, which has become very important in data science and big data analysis. That very often your unbiased estimator, which is what we are kind of indoctrinated with in our textbooks, is actually not that great. It's great, you know, on average it's on target, but on average it could be very far away from that target. You know, this is your target, and these are your estimates. You're on average on target, but in each specific case you could be very far away. Versus if you have another estimator that is a little bit off on average, but is very close to that part, you're actually much closer to the true value than you are with the other one. So that's called the variance trade-off. It of mean squared error to characterize an estimate. So this smoothing idea has to do with shrinkage. And a shrinkage estimator is very famous James Stein theorem that actually took the whole statistics world by surprise when they demonstrated that a biased estimator actually could do better than the traditional maximum likelihood unbiased estimator. Better in a mean squared error sense. So better in a sense that on average the precision was better than the unbiased estimator. And this was very similar to what we're talking about. What if you have groupings of observations and you're trying to compare the means between them? Your estimate of the means will be much better for the larger groups than for the smaller groups. So how can you do, how can you compensate for that? So basically the idea is very simple. The mathematical implementation is very complicated, and I won't go there, not in this class. So the idea is that the overall mean in a Bayesian terminology, you could think of that as a prior notion, has some validity and helps you getting a better estimate in a mean square error sense. So the way you're going to do this is you're going to say, okay, my new estimate, my shrunk estimate, will shrink my crude rate towards the overall mean. And when we have a lot of population, it won't shrink it at all. We'll just leave it as is because it's very precise as is. But when we have a very small population, we'll pull it towards the mean. Now think a second what this implies. We have our Midwestern counties in Minnesota, 0 homicides. What is a good estimate of their homicide rate? Is it 0 or is it the national average? Well, you know, somewhere in between. So how much do we move towards the national average? And that's part of the controversy about these shrinkage estimators, and there's a lot of discussion about them. Principle is very simple. It all depends on the variance. If you have a small population, you have a large variance, you have low precision, a lot of shrinkage, a lot of moving towards the overall mean. If you have a large population, small variance, high precision, basically doesn't matter. Formally, one of the approaches that we will use is called empirical Bayes smoothing. Empirical Bayes as opposed to pure Bayes. In pure Bayes you have a prior distribution, which is a theoretical distribution. In empirical Bayes, characteristics of that prior distribution actually from the data. And so it's a little bit complicated mathematically. I won't go there. The bottom line is that our new estimate is a weighted average of this prior, the theta, which is, in our case, the overall average rate, and the crude rate, which is our R sub I, and the weights are related to the population. So with basically all weight fall crude rate would fall with small populations, all moves to the reference rate. So then we can apply this, 2 different boxes to get your attention. So this is the crude rate. See the red ones are the outliers. Blue is very low. So after we do the shrinkage, they change. They change categories. Basically, what the shrinkage does is it literally, and we'll see this in the lab, it shrinks the distribution towards the mean. So large populations, they don't move. They stay where they are. But the little ones that may be above them get pulled down. So from being outliers, they no longer are outliers. And in the example in the lab, an outlier for the crude rate becomes an outlier because after the shrinking, the distribution has kind of become much narrower. So we see that here. The bottom line of the smoothing or the shrinkage is that your position in the distribution changes. That's the bottom line. And sometimes this doesn't make any difference, sometimes it does. And so if you're interested in actually identifying elevated areas of risk, you might want to take into account this lack of precision. So that's the bottom line. Should we smooth? Should we not smooth? The good thing is it's better in a statistical sense, in a mean squared error sense. With big data, it really is the thing to do. It removes, with a small area estimation, it removes a lot of spurious outliers and it gives you overall more reliable estimates. The counterpoints are that there is a degree of arbitrariness. First of all, what is this prior? What is this reference rate? It's going to make a difference, say in Minnesota, whether you take the national homicide rate versus the Minnesota homicide rate to adjust the rates for individual counties. And if you smooth too much, all the interesting parts are gone. So there's pros and cons of this, and basically where I come from, and I think after a while listening to me, you get this, you just try different approaches and see where the interesting breakpoints are. You know, does it make a difference? Does it change your conclusion? And as I said, in a lot of cases, it doesn't really change much at all. But if you have highly uneven populations, then it does matter. For example, if you work with census tracts are by design supposed to have roughly the same population. So there the smoothing is not going to do too much. But if you work with things like counties, especially urban and rural counties mixed together, then it typically does make a big difference whether you do the shrinkage or not the shrinkage. And actually from a modern statistical point of view, sticking with the old unbiased quote-unquote optimal estimators may not always be such a great idea, and there's a lot to be said to borrow strength from additional information. As we have more information, we should use it to get better estimates in a precision sense.